Welcome to solverfy.
In this problem, we're asked to find the activities of 1 gram of iodine 131 for part A. And in part B, we're asked to find the activity of uranium 238. Some important things to note in order to solve this problem is the thing we're asked to solve, the activity rate, can be defined in terms of a decay constant, which has units of reciprocal seconds, as well times the number of nuclei in the sample that we denote as N. We'll be finding atomic masses of these different substances. However, we'll need to convert them into number of nuclei per sample in order to get a decay rate. For that, we're going to use this conversion factor of 1 atomic mass equals 1.6605 times 10 to the negative 27th kilograms. And also, in order to find our decay constant, it will be helpful for us to have a conversion from days into seconds. Specifically, 1 day equals 86,400 seconds. So for our iodine 131 isotope, it has an atomic mass of 0.906126 atomic mass units. First, we'll find our decay constant. We are told that it takes the iodine 131 isotope has a half-life of 8.02 days. The relationship for to find the decay constant from half-life is the natural logarithm of 2 over the half-life, the time of half-life. And in our case, it's that just over 8 days. Decay constants to answer our question need to be in terms of seconds. So we're going to convert our half-life from days into seconds using that 86,400 conversion factor. Dividing the numerical approximation of the logarithm of 2, which is 0.693, by the half-life in seconds, we end up with 1.00 times 10 to the negative 6th inverse seconds. Secondly, we need to find the number of nuclei that are present in the sample. We're told that it's the sample mass is 1 gram. So we're going to take the atomic mass of iodine 131 isotope in units of atomic mass, convert it to grams using this 1.6605 scale factor times 10 to the negative 24th grams per atomic mass scale factor. Plugging those numbers in, and I remember that I looked up the atomic mass of iodine 131 in Appendix B. Plugging those in, we find that there are 4.60 times 10 to the 21 nuclei. So many nuclei in a 1 gram sample of iodine. So the final step is to multiply this number of nuclei present by the decay constant. And doing that, it was just a simple 1.0 times 10 to the negative 6th. So we subtract 6 from 21, and we're left with 4.60 times 10 to the 15th decays per second. That is the activity rate of the 1 gram sample of iodine 131 isotope. The same procedure goes for uranium 238. It has a molar mass, not a molar mass, an atomic mass of 238.050788 atomic mass units. We will find the time constant for uranium-238, which has a half-life of 4.47 times 10 to the ninth years. So we're, again, need to convert that into seconds. So we're going to multiply our 86,400 seconds per day by 365 days in a year, which I need to put here, days per year. So we end up with seconds, a decay constant which has seconds. That quantity works out to 4.916 times 10 to the negative 8 reciprocal seconds. And finding our number of nuclei in the sample, we're again told we have a 1 gram sample. We're going to divide that by the atomic mass after converting that atomic mass to grams. Plugging those in, we find that we have 2.53 times 10 to the negative times 10 to the 21 nuclei in this 1 gram sample. And multiplying the number of nuclei present by the decay constant, we find that the activity of the 1 gram sample of uranium-238 has 1.24 times 10 to the 4, so about 12,400 decays per second.